Hello everyone. Before I begin, I'd like to thank Sylvia and the other organizers for putting this workshop together. I'm very happy to be here. My name is Newsome, and today I'm going to be presenting to you some details regarding a project I began last year with my advisor, Paul Anderson at Wake Forest University, involving the validity of the semiclassical approximation in 2D electrodynamics. So to outline the following discussion, first I'm going to present an overview, motivating the project direction, then focus on some technical details for the system I will be covering. From there, I will discuss aspects of the linear response theory in its general form, as well as its specific application to the project at hand. Next, I'm going to present a comparative analysis between approximate solutions and numerical solutions to this thing called the linear response equation, as well as some properties of the numerical solutions themselves, and wrap up with a brief discussion and conclusion. Okay, so the semiclassical approximation, generally speaking, treats one aspect of a system classically and another aspect quantum mechanically. This has been used in a wide range of physical situations, some of which I list here. The one relevant for the project here is the decay of an electric field due to the Schwinger effect. The Schwinger effect is a phenomenon by which particles are created by a strong electric field. The original calculation by Schwinger considered a constant electric field, resulting in the following particle production rate gamma. Here, Q and M are the charge and mass of the created particles, and E is the strength of the electric field. Now, this rate will be exponentially suppressed unless this characteristic quantity QE over M squared is at least of order unity, whereby significant particle reduction is expected to occur. Now, in the semiclassical treatment I explore here, I consider a 2D spatially homogeneous classical electric field generated by a time-dependent external source. Through the Schwinger effect, particle-antiparticle pairs are created and accelerate, seen schematically at the right. And this will create a current which will modulate the strength of the electric field. So it's important to note that the model I'm considering here ignores particle interactions. So once they are created, they don't interact with each other. Now, the time evolution of this electric field is characterized by the semiclassical backreaction equation. I give some references here where this has been solved in 2 and 4 dimensions, and I will discuss that equation in more detail in just a little bit. So given the nature of the semiclassical system considered here, a natural question is, when can this approximation be trusted? Or to put it another way, what is the range of its validity? Now, a criterion for the validity was originally developed for the case of semiclassical gravity and later applied to chaotic inflation models with the characteristic dynamical equations for each given by their respective colors here. Here I utilize a modified version of that criterion for the case of 2D electrodynamics. The formal statement of the criterion can be expressed as follows. The semiclassical approximation will break down if any linearized gauge invariant quantity constructed from solutions to the linear response equation grows rapidly for some period of time. Now, later I will formally define what the linear response equation is, but for now, one can think of it as characterizing the stability of the semiclassical equation solutions to perturbations. So note also, this is a necessary but not sufficient condition for validity. So a paper I co-authored with Sylvia and Pepe and others that was published last year and analyzed this situation using a method which approximated solutions to the linear response equation, but subsequently I have solved for the numerical solutions outright. A primary reason for this was I wanted to isolate and analyze the effect of fluctuations on the linear response equation solutions, which could not have been done with only the approximate solutions available. Okay, here I'm going to present some general details about the system under consideration. I'll move as quickly as I can. The action for a 2D massive spin 1/2 field psi coupled to a background electric field is given by the following. I want a JC term here is acting as a classical and conserved external source. The exclusion of this term leads to standard act for quantum electrodynamics. So variation of this action with respect to the background general JQ interpreted as the current density operator associated with spin 1/2 particles. So using the Lorentz gauge, the semiclassical background homogeneous electric field is given by the following, where here the J term in Maxwell's equation is replaced by its expectation value for the semiclassical treatment. Now, since this expectation value is from quantum field operator value, and the size of these fluctuations will directly affect the validity of the approximation used here. The two classical background profiles were chosen for this system, one being a source term electric field seen by the blue curve on the right, and the other being the Sauter pulse given by the yellow curve on the right. These are the two profiles chosen that are coupling to the quantum field. Okay, so in order to get a better feel for what's physically occurring in this semi-classical process, I thought it would be useful to look at the energy densities of the background and spin 1/2 fields, as well as the time evolution of the spin 1/2 particle number. So first, I expand my Dirac field in terms of a complete set of modes, where the B and D are the usual creation annihilation operators associated for particles and antiparticles. The 2D spinners are comprised of the H1 and H2 time-dependent mode functions, with the spatial dependence contained within a plane wave term on the right due to the spatial homogeneity. So utilizing this particular representation for the spin 1/2 field, the Dirac equation will yield a set of coupled first-order ODEs for the time-dependent modes H1 and H2, where the coupling is a result of a non-zero mass term seen on the right. The renormalized energy density and spin 1/2 particle number are given by the following expressions. Both of these quantities depend on the H1 and H2 mode functions in a non-trivial way, and in the next slide, I'm going to plot these. Okay, so the top row is plotting the energy density associated with the classical electric field in red and the spin 1/2 field in blue for the asymptotically constant background field case. The bottom row is plotting the time-dependent spin 1/2 particle number. The left plots are associated with the case of an electric field which is much larger than the mass of the spin 1/2 particles, and the right plots are associated with the case of an electric field which is of the same order as the mass of the spin 1/2 particles. One can notice for the top left plot, both energy densities oscillate rapidly, continuously giving and receiving energy from the other. This will correspond to a relatively large numbers of created particles seen by the spin 1/2 field particle number plotted in the bottom left, but their characteristic lifetime will be relatively short, where roughly something like 95% of the created particles on average are gone within a few time steps through the first oscillation. The top right plot indicates large permanent growth in the spin 1/2 field when the electric field is of the same order as the mass, where we see for late times, we have exponential growth appearing. And this gives us more of a sense of permanent particle reduction seen in the corresponding bottom right plot. And this, I think, will be useful to keep in mind for the stability analysis I'll present in a little bit. Okay, so to understand the stability of the system in the context of the validity of the approximation I'm using here, I'm going to turn now to some linear response theory. So formally, the linear response equation can be derived by a second variation of an appropriate effective action. But if one takes the semi-classical backreaction equation and perturbs it about a background solution, this results in the linear response equation as well, which as I said previously, characterizes the time evolution of perturbations to the system. The interesting piece here is the perturbation of the quantum expectation value of JQ. So before I get into the specific details of this term, I thought it would be useful to very briefly review a crucial element of general linear response theory. So the induced change or perturbation of any quantum expectation value can be expressed as a space-time integral over a source term driving that change multiplied by a term relating the two. Now, this term in red is acting as a generalized susceptibility, which is causal and can be expressed as the expectation value of the commutator of the observable at two distinct space-time points. Hence, chi in this sense is a retarded two-point Green's function for the observable O. So now the linear response equation, which I have again boxed in the top right, again involves a perturbation of an expectation value. And the expression for the perturbed current expectation value is given by the following. We can see the usual space-time integral over the commutator discussed generally on the previous slide, but the other term, the first delta A of t piece, this originates from the renormalization of the current expectation value using the standard WKB regularization method. The spatial integral of the correlation function can be expressed in the following way, where under the mode integral, we have the imaginary piece of a product of the H1 and H2 mode functions at different times t and t prime. Recall these are the time-dependent mode functions coming from the specific representation of the Dirac field that I'm using. So it's useful to explore the massless limit in which the electric field is much, much larger than the mass of the spin 1/2 particles. In this case, the H1 and H2 mode functions can be expressed analytically as modified plane waves, which will ultimately cause the two-point function to vanish. This will yield a sourced harmonic oscillator for the linear response equation solution, which will be bounded. Now, this gives a clue that towards the massless limit, the semi-classical approximation based on the aforementioned criterion should be valid, since rapid growth in the perturbations is not possible. Let's see. So in the article I co-authored, which I mentioned previously, we initially used a method to approximate solutions to the linear response equations, seeing how it's a second order integral differential equation. Having obtained the numerical solutions outright, however, I thought it would be useful to take a slide or two just to compare those results. The method to approximate the linear response equation solutions works by taking two solutions, what I call E1 and E2. These are solutions to the semiclassical backreaction equation, which have initial conditions differing by a small amount and have their difference represent a perturbation in the electric field. Now, for the finite difference to accurately approximate the perturbations in the electric field, it must hold that the finite difference in the expectation value of the spin 1/2 current accurately approximate the corresponding perturbation in this term. Now, the finite difference of the average current terms can be expressed by the following. This is complicated, but here, just note that the subscripts 1 and 2 that I'm using represents quantities associated with the nearby semiclassical solutions, E1 and E2. Comparing this to the expression for the perturbation in the average current, one can see that the first term, the first terms in each have a good chance of being associated with, assuming that the semiclassical solutions are close enough. But the non-trivial second terms in both equations are harder to associate with one another and might not be well approximated for certain cases. So some plots of these cases are given by the following for the asymptotically constant background field case. And all the plots, the approximate and numerical solution, the numerical linear response equation solutions are given. The red curve is the approximate solution and the blue curve is the numerical solution. Now, the top left plot represents the large field to mass case, and the bottom right represents the case of an electric field strength of the same order as the mass, with the other plots being two different intermediate cases. Now, for the small mass case, the two appeared to match quite nicely, but as one approaches the critical scale where QE over m squared is 1, that you can see that they separate quite quickly and are only they only closely resemble each other for very early times. Now, it was a good thing then that in the article that I co-authored that we focused our analysis only on the early times where the approximate and numerical solutions seem to agree, and before significant quantum particle reduction has a chance to affect the system. Okay, so moving on. So here I'm going to present just some preliminary numerical solutions to the linear response equation by themselves. So I have partitioned the solution into its separate classical and quantum contributions. Since the classical portion of the solution can be shown to never grow without bound, in order to analyze the stability, I have isolated the portion of the solution stemming from the quantum effects. So on the left is a semi-log plot showing the quantum part of this linear response equation solution for the asymptotically constant background. I'm representing 3 different cases, one corresponding to a large electric field strength compared with the mass of the spin 1/2 particles being the blue curve, the critical scale being given by the yellow curve, and an intermediate case being given by the red curve. Now, notice for the small mass case, there's bounded oscillatory behavior, which is to be expected given the 2-point function on the previous slide was shown to go to 0 towards the massless case. But for the critical scale where QE over m squared is 1, there is a significant exponential growth. Now, based on the validity criterion stated previously, it appears that the semiclassical approximation is not valid near the critical scale, but tends to become more accurate as the strength of the background electric field grows larger compared to the mass of the quantum particles. Now, the plot on the right shows the same situation, except for the Souter pulse background field case. And there are some subtle differences in the behavior of the curves, but the overall qualitative behavior is the same in terms of the growth of quantum perturbations, especially the critical case where we see exponential growth. Now, previously I showed that towards the massless limit, the H1 and H2 mode functions become these modified plane waves and cause the 2-point function to vanish. This left the linear response equation having bounded oscillatory solutions. Therefore, it must be the case that the presence of a non-zero 2-point function in the linear response equation leads to the unbounded exponential growth at the critical scale. So here I present some plots of the spatial integral of the 2-point correlation function for the asymptotically constant background case. This is for the critical scale, or I'm sorry, no, I take that back. The horizontal axis is over the time variable t prime, where the value of time t is equal to 100 for all 3 cases I'm considering here. Now, the large field to mass case in blue is small as expected, and the intermediate case in red is larger, but doesn't seem to have any distinct behavior. But the critical case where QB over M squared is equal to 1, we have approximate exponential growth in the amplitude as the points T and T prime come together. This might roughly have the interpretation that of if the perturbation in the background field occurs, the correlations between measurements of the spin 1/2 current drop off exponentially to some minimum the longer one waits to take like a subsequent measurement. Okay, so this will be my last slide. So to summarize what I've shown you, I have implemented a criterion which originated in semiclassical gravity to test the validity of the semiclassical approximation in 2D electrodynamics. The criterion states for the semiclassical approximation to be valid, the semiclassical equations characterizing the system should be stable to linearized perturbations. Obtaining the numerical solutions to the linear response equation reveals that when the electric field is much larger than the mass of quantum particles, the semiclassical approximation appears to be valid. And when the electric field is of the same order as the mass of quantum particles, the approximation appears to break down. Now, some physical implications one might be able to draw from this are when looking at the time evolution of the energy density or particle number for the spin 1/2 field, for the critical case, there's a sense of permanent particle production compared to like when you're going towards the massless limit. This case leads to a maximization of the 2-point function for the quantum current, leading to exponential instability in the perturbations of the average current value. Thus, the semiclassical approximation seems to be good when the electric field is large and bad when it is small compared to the spin 1/2 particles. And that's what I'd like to leave you with. So I thank you for your attention and we'll take any questions at this time.
Okay, thank you, Ian, for this very nice talk. And questions, comments? Sylvia, is that question? Yeah.
Yes. Hello, Ian. Congratulations for your talk. I liked it a lot. So I wanted to ask you, because you said that the criterion is most violated in this limit in QE0 divided by M squared equal 1. But then it seems that when you increase the mass, the fluctuations are lower. The semiclassical approximation is better, no? For the massless limit is better, and for the supermassive limit is also better than in this intermediate case. So do you have any idea about this? Why?
Well, yeah. So I mean, if you're talking about the case where, say, the mass is just increasingly larger than the electric field strength, like just take the limit that the electric field strength, is minimal compared to the size of the mass of the particles. What you're going to have there is you're going to have less and less particle creation events occurring, right? Because it takes so much more energy from the electric field to actually produce a particle-antiparticle pair. And in the extreme case where the electric field essentially goes to 0, you're going to just get back like classical electrodynamics, because you're not going to have essentially any particle production. So it does seem like it towards the massless limit where the electric field is larger, much larger than the mass of the particles, you have the least violation of our criterion. And I think the other way works as well, because you're going to get just back to classical electrodynamics. So it seems like there's a special threshold where where this exponential kind of divergence in the perturbations occurs around this critical scale. So yeah, that's right.
Okay, thank you.
Yep.
Okay, thank you.